Okay. Well, hi everybody, my name's Ken Graham. That's me without a beard, this is me with a beard. You make your minds up with a lot, it's thinking better. So this paper came as a result of a Master of Science thesis that I completed last year on sustainability in practice, and it's very much aligned to commercialism, what's actually happening right now in the marketplace. I appreciate a lot of the papers are to do with theories, and that's where everything starts. This is more sort of like at the coalface, what's happening right now in our markets. So the first thing I want to share with you is that I actually surveyed a lot of architects and interior designers, and I very soon became aware that there was a disconnect, their understanding of environmental product declaration. Now we know that the identity cards are products, but there is this definite low understanding among specifiers. They regard them as confusing and difficult to understand, and I think you're all aware, if you know EPDs, very difficult to compare like with like, there's variances all the time. There's definitely limited research into EPD reliability and life cycle analysis aligned with building lifespans. We seem to just take a starting point view on a lot of building projects. We don't often think long term. So I've tried to address this by looking at the whole of life carbon footprints of buildings and analysing EPDs. So the purpose of this is basically to establish awareness and understanding of EPDs for interior flooring options. I've just used that as an example. You can use this methodology for any material type, any building component, and obviously to critique the EPDs and propose improved building lifespan assessment processes. I also think that we need to correct and close information and knowledge gaps by continuing to guide, educate and encourage specifiers to adopt a design and build for life ethos. Everything that we do, everything that we try and present to the marketplace, they struggle to understand the starting point, the midpoint and the end point of a lot of products and materials, and the better we make that clearer, I think the better we'll do for achieving the goal of reducing the CO2 carbon footprints. Now I've focused on the UK, this applies to all countries of course. So I'm sure you're all aware of this. This is your typical process going through the life cycle assessment. We start off with the A1, A2, A3s. That's very much getting the material made. That's the embodied carbon, really the locked-in carbon of a tangible physical object or material. Then we've got the building phase. We transport, and if it needs installing, we've obviously got an installation footprint, which is A5. And then we've got B, which is all about maintenance, and C, which is all about repair and reuse. Now, embodied carbon is very much a business focus. Organisations should understand what their embodied carbon footprint is because they make things. They should know these things. But you'd be surprised at how very few people understand operational carbon, actually what's happening down the track once the building's operated. Now this is a typical donut chart of where carbon appears in a building lifespan. Obviously when we first build a building it's all embodied, that's the orange part of the bar, but over time as the building's being used we catch up with operational carbon. So obviously we heat it, we light it, we operate it, we maintain it, and then we have an afterlife. And we're always focused on trying to reduce carbon footprints at that embodied stage. But what I want to do is just think about the whole building lifespan and take into consideration maintenance and operations. So it's very simple to understand, but nobody's really thought about how we can actually map this out in a simple way. So if we think about cumulative emissions over the lifespan of a building, and we think about the product life cycles within the building lifespan, obviously when we start off we've got a product, a tangible product, A1, A2, A3, that's its embodied carbon footprint. Then we need to install it, so as an installation carbon footprint, and then over time, and obviously depending on how long its lifespan is, we have a maintenance footprint. And this could be everything from obviously cleaning fluids, chemicals, energy use, even the generation of steam. And then, importantly, at the end of that product life, we've got a recycle and circularity factor that we need to take into consideration. And we're not really capturing this as well as we should in this sort of linear model that we operate in this world. So I actually think this footprint cluster is crucial, but we do tend to focus just on embodied. We don't really think about the operational carbon footprint. I really do believe that simplicity has been replaced by complexity. One of the things that we've done is we've added an awful lot of mixed molecules in a lot of the products that we produce. I've heard a lot of talks today about adding things to materials. As soon as we add things to materials, we make that material complex. The easiest way to recycle a material is keep it simple in the first place. Does that make sense? Yeah. So it's just crazy how we introduce all of these things. To the extent in the UK, only 1% of all vinyl flooring in the UK is recycled. Only 2% of all carpets are recycled in the UK. And that's because we're mixing all the polymers in terms of the construction of the material, and then we contaminate it with any adhesives. So by constantly adding and adding and adding to materials, the construct, the way they're installed, and the way they're operated, we're constantly adding problems to the ecosystem. Yet for aggregates in the UK, just an example, there's a 93% repurposing rate for durable mineral aggregates that we recover at resource centres, at recycling centres. It's used for aggregate, very inert material. And another thing that I found in the research is that there's an awful lot of pre- and post-consumer recycling confusion and circularity doubts. One of the biggest flaws we've got in our industry is the phrase that gets used, pre-consumer recycled content. You will see this mentioned all the time. Companies advertise their products as having recycled content. We all assume it's post-consumer, but the majority of it is pre-consumer recycled content. Now that's an oxymoron. How can something be pre-consumed and yet be a recycled content? Recycled means it's had its life. Pre-consumer means it's not had its life. There's a lot of confusion out there. And what I've also found is there's a lot of effort being placed on the SDGs and corporate social responsibility reporting in the industry associations. Some are ahead of the curve, some are way behind. So I want you to get thinking about this. If we think about the product life cycle, it's pretty straightforward. It's in the EPD, A1, A3, A5, B1, B5, times the number of times it's going to be cleaned over its life cycle or for the whole of its life cycle. And then we have the recycled content. And then quite simply, we just work out, well, how many product life cycles will there be within a building lifespan of, say, 60 years, which is the norm. So we end up achieving a building life cycle carbon footprint. And I think really, if we sort of like expand this, you can see the sort of products I'm talking about. I should actually add a bit of a caveat here, that I've just focused on these products with these EPDs. Obviously there are many products out there from similar product categories with very different types of EPDs. And of course many of the new technologies that are available, they may not have EPDs yet. So it's all about EPDs. So if we just start off with our lifespans, you can see straight away that has a bearing. How long does a material last for? We must consider that. And then what is its initial A1, A3 embodied carbon footprint? We have to take that into consideration, obviously. And then we start to add A4 and A5, and then we get into the Bs, all the operating carbon footprints. And then finally, we need to add the afterlife carbon footprints, what actually happens to these materials. Now, once we've got all of that, once we know the big picture, we then simply need to know how many times that product will be replaced over a building lifespan. And then that's the multiplier. And that gives us an indication of what the starting point embodied carbon footprint and long-term operating carbon footprint will be for materials over a building lifespan. And it's quite alarming when you actually look at this. This is, for example, one end of the scale, one of the textiles. I'm just using a polyester carpet profile, for example, here. Aside of the VOCs that we know they have, when we actually look down at the number of maintenance cycles are needed, how much water is consumed, how much energy is consumed, you can very quickly see just how much the carbon footprint adds up. Then we look at the afterlife, what happens after the carpets have been used. Sadly, I'd say only 2% of recycling in the UK, about 75% are actually incinerated. We make electricity out of our used carpets. I guess you could call it a modern coal. And that's the sort of footprint that we get from incinerating the carpets. All of this is in the EPD. Whereas, now if we don't map that over time, we start off with our initial 10-year period. We've got our A5 installation footprint, A1, A2, 3 embodied. Then we've got our operating carbon footprint, and then we've got our C1, C4 end-of-life carbon footprint. And then after that period, we start again. So every 10 years, we're replacing this material to the extent that once we get to the end of the building life cycle, 60 years, that is the typical carbon footprint that's going to be generated by choosing that particular material. If we go now to the other extreme, one of the hardest materials I can think of, I guess, is the ceramic tile. Using the same approach, you can see here, it's got very low maintenance. So that actually has a big bearing. The fact that a polyester carpet has a carbon footprint 33 times greater than a ceramic tile for maintaining it, to me, is quite alarming. And then we look at the afterlife. Because a tile is inert and it becomes an aggregate, it's totally inert, safe, no VOCs. It can go back into the ground and be used as an aggregate. As a result, its carbon footprint is much less. A carpet is 38 times greater. So I'm just using these two as extremes just to explain the point. And this is the corresponding chart that we get for a ceramic tile. As you can see, it's got a completely different shape. So I just want to emphasise these shapes for you. Let's start off with the one that appears to have the lowest based on that EPD. 15.79 kilograms of CO2. Incidentally, you're probably aware a kilogram of CO2 is a metre squared ball. So just think of this as 15.79 balls per square metre over the lifespan of a building. That's 1 square metre. And we know that there's this short-term thinking that we've got we have a problem with making things last through fashion, through trends. We tend to switch interiors out, which itself is a flaw. Now we have engineered wood laminate, and you can see that it's got a lower carbon footprint, and it just steps up after 50 years. Cement tiles, these are known as terrazzo tiles, I think, in the industry. That's got a similar carbon footprint. Solid wood is at 30.35, hemp wood at 32.81. You can see the picture here, and what you'll soon start to see is that once we start moving away from the natural, durable materials, and we start moving in, I guess, into the world of plastics, you'll see that these carbon footprints start to significantly increase. So there's a big gap here. There's a big gap between durable materials and using soft textile. I've only talked about 1 square metre. Nobody builds a building with 1 square metre. Let's use an example of 2,000 square metres, just as an example. So let's put 2,000 square metres down. So those shorter product life cycle materials like plastics. The worst one is the hybrid plastic large carpet tile. 341 tonnes of CO2 will be generated over the lifespan of that building in that 2,000 square metre project. Let's now move down to polyester carpet, slightly less with 235, nylon tiles with 197, LVT tiles with 132, vinyl roll 96. Now we'll move over to the longer product life cycles, ones that last longer, more nature-based. We've got wood fibre laminate at 112 tonnes, linoleum at 92 tonnes, rubber tiles at 81 tonnes, cement tiles, terrazzos at 35.94 tonnes, and the lowest is ceramic tiles at 31.58 tonnes. So what's the difference? Well, it's 310 tonnes of CO2. That's what the difference is. And we're supposed to be reducing emissions on the planet. So I think there's a good story to be told for actually reducing these footprints by thinking long term. Without a doubt, the building industry is at a tipping point. They're all confused out there. They don't fully understand what they're doing, how they're going to do it. There's very few regulations out there, a lot of it's voluntary. Yet we know there are going to be additional buildings required to cope with climate migration for one thing, and to cope with the fact that our climate is changing and our infrastructure won't cope with those extremes. So we know there are going to be more buildings. However, we're going to be relying very much on EPDs. Yet we know that they have low awareness of them. So there's this requirement for more building, and yet there's this requirement to reduce the carbon footprint of all these buildings. So we need to understand these flaws, I think, within the EPDs. We're not really emphasising these building life cycle components or materials. I don't think we can be blinkered and assume all is perfect. We know the EPD format is not standardised. There's incomplete data. There's different types of EPDs, and the units of measure can vary. However, this is it. They're the only identity card we've got in our sector to tell us what's going on in the building. So even with the data strengths and weaknesses, they still remain the most critical documents in determining carbon footprints. So I believe that, just again, this is just focused on the internal flooring. We can go in many areas of the building, but I think they need to be better aligned with the lifespan of a building. We need to adopt a design and build for life approach if we're actually going to reduce some of these emissions. And we know that our environment is struggling to cope with our overconsumption driven lifestyle. We all know there's planned product obsolescence out there, and it's not just our clothing in our smartphones, it's actually the things we walk on and the curtains we use and the seats we sit on. It's everywhere. And we know that consumer problems have created circularity and recycling challenges, I have to say, rather than solutions. I'm a fan of circularity, but we shouldn't be forever producing products with small circumferences, because every time we try and recycle something, we add risk. It might actually get there and make it. The larger the circularity curve, the better. So I think the sustainable values need to be better understood. We need to realise longer-term environmental gains and losses from material selection, and we need to challenge this lower cost on short-term leasing mindset and align product life cycles investments across the whole building lifespan. So essentially, the basis of my thesis is we need longer life materials down there. They need to be aligned with neutral design, provide greater sustainability value ahead of shorter life materials that are aligned with trend design. We really need to try and break this model. These are all the references that were included in my paper. These are all the EPDs that I'll use. Again, I mentioned the caveat before, and I acknowledge that this is a commercial market. If you've got some amazing new products that are coming out soon, great, get them in the market with an EPD and let's analyse those. And that's it, folks. Hope you enjoyed it. Any questions at all?
Thank you.
Excellent. Thank you very much. Exciting presentation.
Thank you.
I may have a question, but before my question, anyone?
I may have like a comment, it's not a question.
Yeah.
Well, yeah, you did a great job like in analyzing all the materials, the internal flooring. I think you went to the easiest part. How about the facades?
Exactly, yeah.
The facade is like, it must be trimmed, it must be glass, it must be curtain walls.
Yeah, yeah.
Like the flooring, it's easy to adapt it.
There's a lot of variation in flooring. Yeah, for my thesis, I just focused on one thing that we're used to, and we see it all the time, we walk in it all the time, and it's a very, very good example to use in terms of the way that we need to shift our mindsets from when we're outside and we're in public, we're familiar with hard surfaces, they're durable, and we've got this mindset that hard and durable means public, uncomfortable, cold. So it's almost like, and this is all countries, it's almost like we've adopted this mindset. When we go indoors, it's going to be different. It's got to be cosy and warm and textiles everywhere that wear down. So it's a very good material to choose to really, I guess, emphasise the problems that we've got with buildings.
Yeah, but no, my question is about the material being used on the facade.
I could look at...
What would you suggest then?
I could look at that and analyse. If the EPDs exist for facades, you just go through the same process.
I see. I know
Same
the methodology is
methodology.
very clear and brilliant, fabulous. I'm just asking, like, what's your vision? Like, if we change with like from carpet to less ceramic to...
You want my personal view?
Yeah.
Right, on facades?
Yeah, for example, particularly in the UK.
Well, I would say that we don't take into consideration north-south orientation as well as we should, for a starter. We don't make use of natural wind currents, normal wind eddies with facades to get natural cooling. I really don't think that and there was a lady speaking earlier on about this, I don't think we understand enough about the thermal transference of energy, like whether or not, like, for an example, in here, we could actually be using a south-facing wall to absorb heat and then use a heat transfer system to throw that warm air to the cold side of the building. And that would require some sort of ducting system. Obviously, it would be great to be able to shift the colour scheme of facades. So in winter, we have a dark material to absorb heat energy, and then in summer, we have a light material to reflect heat energy and have free cooling. But hey, that's a whole different subject.
Yeah, different subject. Yeah.
Any other questions?
Yeah. Question? No?
We're good?
I have
sure.
a question. So, it's quite interesting topic about calculation CO2 footprint, especially flooring you calculate, maybe walls and roofs will be calculated. And then my question is not that. My question is, how do you define the life of house or life of buildings? Because in European building, I think life of house is 100 years or more 100 years. But I'm Japanese, and in Japan, that is scrap and built. For example, Singapore, scrap and built. Maybe the life of house is 30 years.
Yes.
In that short period, how do you think is that calculation?
Well, again, I've used 60 years as an example. So with that model, instead of putting 60 years as the normal building life cycle or lifespan, I should say, for that country, you change it. So it would be 30 years or 40 years or 50 years. Well, 60, I think, is too low anyway. If we design right and use the right materials, it should be around much longer. We're going to need it because we're going to run out of materials. Okay, any other questions, Jogo? All right, thank you.
Yes, thank you very much.